Hello, my name is Alysha Helmrich, and I am the host of this week's Future Cities podcast. I'm a doctoral student in sustainable engineering, studying how infrastructure managers can create more resilient infrastructure by expanding physical and institutional capacities. This week's episode is a slightly new format. Myself and 5 others are discussing a research project that we have been working on the past year, titled Using Biomimicry to Support Resilient Infrastructure Design. The audio you are hearing today was primarily recorded for a short video series, but I will be here to navigate you through it. First, we will drop in on a conversation between 3 individuals you've met before, Dr. Sam Markoff, Dr. Nancy Grimm, and Dr. Mike Chester.
Hello, I'm Dr. Sam Markoff. I'm an assistant research professor in the Department of Civil, Environmental, and Sustainable Engineering at Arizona State University, where my research primarily focuses on urban infrastructure resilience to extreme events like flood and wildfire. I am joined today by Dr. Nancy Grimm and Dr. Mikhail Chester to discuss what exactly is resilience. And before diving into that, I would like to give guests a chance to introduce themselves. So first we'll start with Nancy.
Hi, I'm Nancy Grimm. I'm a Regents Professor in the School of Life Sciences at Arizona State University. I'm an ecosystem scientist, but I work in interdisciplinary teams studying cities and their resilience and envisioning their futures. I was founding principal investigator of the Central Arizona Phoenix Long-Term Ecological Research Project, and now I'm co-directing the Urban Resilience to Extremes Sustainability Research Network, which we call UREX for short, and then a new international network of networks called Natura, which is focused on synthesizing knowledge about nature-based solutions to urban resilience challenges of the Anthropocene.
Great, thank you, Nancy. And Mike?
Greetings, my name is Mikhail Chester. I'm a professor of civil, environmental, and sustainable engineering in the School of Sustainable Engineering and the Built Environment at Arizona State University. And I'm a civil engineer by training, but I run a research laboratory that focuses broadly on questions and solutions to preparing infrastructure for the challenges of the coming century. We do a lot of work around climate adaptation and the reliability of infrastructure under extreme events. I'm also the director of Arizona State's Metis Center for Infrastructure and Sustainable Engineering, and I'm an executive team member of the Urban Resilience to Extremes Sustainability Research Network.
Great. It's wonderful to have you both here today. And that brings us to the main topic of discussion, resilience, and what exactly resilience is. So resilience is becoming an increasingly prominent and popular topic across several disciplines. However, there is often a lot of difficulty actually defining it. In fact, it is sometimes easier to identify what is not resilient rather than what is resilient. So Nancy, I was wondering if you could maybe start our conversation off and describe a little bit about how ecologists historically have thought about and defined resilience.
I actually feel like I've been working on resilience for my entire career, which is a pretty long one. So some of the earliest conceptual framings of resilience that I recall from my work as a graduate student studying stream responses to flood disturbance were that resilience was the rate of recovery after a disturbance to the pre-disturbance state. And that was viewed as one component of ecosystem stability, another being resistance, the ability of a system to withstand disturbances. So in the case of a flood in a stream, the riparian trees along the side of the stream might represent resistant ecosystem elements because they're large and they're rooted, whereas algae, another type of primary producer in the system, would represent a resilient element because even though they get scoured and washed away by the flood, they have low resistance, they regrow rapidly, so they have high resilience. Now, that framing, which I actually used in my dissertation, began to shift when ecologists recognized that ecosystems are almost never at equilibrium, but rather they're constantly changing. So a newer concept of resilience was introduced actually way back in 1973 by Buzz Halling, and he actually incorporates both older terms of resistance and resilience and refers to instead the capacity of a system to maintain its structure, its processes, its basic identity, and the feedbacks that contribute to its organization across various kinds of stresses, shocks, or what we call in ecology presses, continual drivers of change, and pulses, which are abrupt disturbances that are continually experienced by these ecosystems. So as the concept has evolved in ecology, especially when we bring in perspectives from social science, ideas of adaptation, relatively small tweaks in the system, and even transformation, where the entire landscape of stability states that can be occupied by the ecosystem shift, these have begun to be incorporated into the framework. And finally, we also have recognized the need in social ecological systems to ask resilience of what to what, when, and for whom. And this specifically addresses the challenges of incorporating human and built elements into the system.
Great. And Mike, how does this compare to your experiences with resilience in the engineering domain?
I would describe resilience engineering as a fairly new and evolving topic in some ways. Resilience in engineering seems to be less well developed than in the SES and STS communities, the social ecological and social technological systems communities. We've seen resilience as a concept in engineering take off in the past roughly 5 to 10 years, which largely coincides with efforts to protect infrastructure from climate extremes and a number of notable national, US, and even global efforts to focus on adaptation. We see resilience engineering heavily being discussed in the climate adaptation communities, but seems to be somewhat less well developed when it comes to other dynamics or hazards. I think it's somewhat useful to take a step back and look at how resilience in engineering has evolved. The concept isn't all that new. It first emerges in engineering with the design of warships in the early 19th century. By the 1960s, though, we're starting to see engineering using the term to mean specifically the capacity of a material to absorb and unload energy. And that definition has persisted for a long period of time. Until recently, resilience in engineering was dominated by this bounce back framing. So you've got a system that's going along at about 100% capacity, and then it's perturbed. It drops below 100% capacity and then slowly comes back because of sort of intervention and things that we do to bring the system back online, where the shape of that curve is actually really important. Problem that we're seeing is that, and now several scholars are actually addressing, is that resilience cannot be simply synonymous with bouncing back after taking a hit from a hazard. And that's partly because we can't always hold back the hazard, especially if it's uncertain and likely growing in severity, such as in the case of climate change extremes, and because we don't always know what the hazard is or how our engineered systems are going to perform. As such, we're starting to see resilience engineering framings that are starting to align with definitions in the more advanced SES and STS communities, their resilience framings, which tend to focus on principles of adaptation and transformation of the systems.
So given this kind of parallel thinking and increasingly convergent thinking about resilience in ecology and engineering, Mike, I was wondering your thoughts on kind of moving forward. How do you see the field of ecology informing and complementing resilient infrastructure design?
It's become clear that resilience encapsulates or should encapsulate social, ecological, and technological / infrastructural dimension, that there's interplay between those domains that if recognized and leveraged can lead to very different recommendations than if we simply focus on any one domain. Infrastructure resilience has for a long time emphasized armoring, strengthening, or hardening of the asset to hold the environment back. And as we think about new ways to deliver services by infrastructure in the face of changing conditions, as engineers, we're trained to never let failure happen, but natural systems don't follow this concept. What is around is adapted and transformed to be successful. With other systems having died off, engineers don't typically take this view. So we, in our biomimicry project, decided to do a deep dive into the concepts around biomimicry and ask whether there are design principles that could be extended to infrastructure. Biomimicry, for me, is one of a number of candidate new ways of thinking about how to change how we approach infrastructure adaptation.
Yeah, I agree with that. Biomimicry is new to me, but I think there's some promise. What I understood until now to be the purview of biomimicry was copying the adaptive design of organisms that have evolved through natural selection to be perfectly adapted to their environments. And that adaptive design is so much the case that in ecology, we ask for frequently disturbed systems like streams, whether disturbance is even disturbance in the context of organisms that have evolved to live there. Elements of our built environment certainly could benefit from copying species adaptations in nature. But perhaps there also are some things we can copy at the ecosystem level, that is all the complex of organisms and the abiotic environment together in a system, as we seek to make our infrastructure more resilient. So taking lessons from the inherent resilience of natural ecosystems in the face of this ever-changing and disturbance-driven environment that they experience.
Great. So all of us are very much familiar with the growing complexity and shape of the hazards and threats facing our cities and our infrastructure system, which in turn has highlighted the need to think across disciplines. So it's really encouraging to see an approach like biomimicry serving that process and sort of forming a way to kind of bridge ecology and engineering, and is a really exciting example for some of the possibilities that multidisciplinary research can bring. So Nancy and Mike, thank you very much for your time and for your insightful comments about where resilience thinking came from and, more importantly, where it's going.
You're welcome.
Thanks.
What a great conversation exploring the term resilience. Thank you for leading that, Sam. Next, we are going to hear from Dr. Cheryl Desha and Dr. Sam Hayes from Griffith University in Australia. They will introduce us to the world of biomimicry.
Hello, it's great to be with you. My name is Cheryl Desha and I'm an environmental engineer at Griffith University in Brisbane, Australia.
And I'm Samantha Hayes. I'm a consultant and researcher in sustainable construction and biomimicry in Brisbane, Australia. And we wanted to take a few minutes today to run through with you a few key ideas around biomimicry. So starting with what is biomimicry, then starting to look at what applications there might be for biomimicry in engineering and how those applications and ideas might benefit the design of our cities and our critical infrastructure. So biomimicry as a term, the word, comes from bios, meaning life, and mimesis, meaning to imitate. It's a design discipline that really looks to draw out nature's best design ideas and concepts and apply them to human design challenges. And it's based on the premise that life on Earth has existed for almost 4 billion years, and that during that time, organisms and ecosystems have been testing and adapting and refining design strategies in response to a lot of the same challenges and operating conditions that we're now trying to address in our design and engineering solutions. So things like climate change, resource scarcity, a whole range of different operating constraints that we're designing for now. Different organisms and ecosystems have already had to adapt their design approaches to those various challenges. The idea is that we can essentially take a bit of a step back, adopt a bit of humility and look to those systems and see where we can learn from them. If we were to squeeze the history of the universe down into one calendar year, we would see that life on Earth appeared around September. Humans arrived at 8 p.m. on New Year's Eve, and the first human settlements arrived about 20 seconds to midnight.
So what we'll look at now is the applications that biomimicry has to engineering and what examples we can learn from in terms of infrastructure design. We'll give you a brief explanation of learning from nature at the level of form, process and system levels, and think about what that means for infrastructure and design. Let's think about this in relation to a popular example of the Shinkansen, or the bullet train in Japan, and how that was able to benefit from a bit of creative thinking on part of the engineers. So if we take the Shinkansen, it was the fastest train in the world at the time of its design and production, going at 200 miles per hour. But the air pressure changes as the train would pass through tunnels caused such a big thunderclaps or pressure differences that the residents up to a quarter mile away would complain and the windows would smash. Not a really great solution for long term. However, the train's chief engineer and very creative fellow was actually a bird watcher, and he asked himself, is there something in nature that actually travels really quickly and smoothly between two very different density mediums? And with that in mind, they were able to model the front end of the Shinkansen on the kingfisher bird, which dives from the air into bodies of water with very little splash to catch fish and then emerges to perch on a branch, quite happy and able to do it again. So really quite energy efficient. They were able to achieve a noise reduction and avoid that pressure change situation. They actually used 15% less electricity as a result, and the train moved 10% faster. So a really great win-win-win solution as a result of some creative engineering that took inspiration from nature. There are other examples around tree and bone growth with structural optimization. You might look at oyster shells with some tough structural composite materials, the spider web around concrete reinforcement and configuration, and even leaves and insect wings around cantilevered sheets.
That's such a good example, Cheryl, because it shows how simple some of these ideas and applications can be. That concept, that functional performance outcome, has already been refined over tens of thousands of years. And we don't need to now go and redo that work. We can look to where those design parameters have already been optimized. Similarly, so beyond that form level, where you're looking at the shape and the form of an organism or part of an organism, the next level then is looking at process. And so that's drawing on processes that we see in natural systems. Things like biomineralization, self-renewal and self-repair. So those are ideas, for example, of self-renewal and repair. They're things that we see everywhere in natural systems, but we really very rarely see in engineering. So how can we start to design infrastructure and materials and products that can internally sense vulnerability and damage and then initiate self-repair processes? That sounds like such an exciting concept for our built environment, and it's something that is really quite standard within our natural environment. There's a lot of work underway at the moment looking at materials like concrete and asphalt and trying to develop these self-repairing materials so that moving forward, the way that we operate and maintain infrastructure in our cities could really be quite dramatically different. Similarly, at the system level, there's a lot of work underway to look at how we can learn from ecosystems as a whole and how organisms operate within the context of a broader ecosystem. So, for example, looking at across ecosystems globally and drawing out specific design patterns. So things that we see consistently in nature that we might be able to draw into our design patterns and approaches in the built environment. So in nature, we see things like self-renewal and repair. We see a lot of closed loop systems with waste recycling and reuse. We see an ability to adapt and evolve. So these principles are things we can learn from in engineering as well. And even looking at how we measure our performance. So in ecosystems, we see that performance can be measured by regenerative ecosystem services that are generated. So what if we started to measure our cities against a benchmark of how an ecosystem would perform? What services and benefits? It's a very different way of thinking about urban design.
Thanks, Sam. So when we think about that opportunity suite of benefiting from thinking about nature in our designs of cities and our critical infrastructure, I think the challenge and the opportunities there for the engineering community and the built environment community together to create those win-win optimal solutions is really substantive. It's super important then that we can, in a methodological way, in a rigorous way, take that inspiration from nature and turn it into a process of inquiry that leads us to solutions that are really holistic in their considerations and beneficial in their outcomes. So having nature as a context guide us in strategies for responding to that complexity and uncertainty is very exciting, and also we need to be rigorous in that approach. So today, hopefully you've been able to learn from our short discussion around what biomimicry is, what it looks like in an engineering context, and how it might contribute to the design of resilient cities and their component infrastructure. Thank you.
Thank you.
An excellent overview. Now I'm going to deep dive into our research and findings. Infrastructure consists of systems that support the institutions and services that maintain our functioning society. These systems are becoming increasingly complex while working in a deeply uncertain world. Yet infrastructure systems are not the only systems trying to deal with this new dynamic. natural systems do as well. In ecology, resilience is the expected or unexpected disturbance a system can absorb while still functioning in a dynamic equilibrium. Biomimicry, or emulation of nature and design, has provided inspiration to designers for a very long time. Oftentimes, we see emulation on a form or process level. However, we can also mimic ecosystems. In 2013, Biomimicry 3.8 developed a list of characteristics that contribute to the resilience of natural systems, and they called this list Life's Principles. There are 6 different principles on this list, and they have various sub-principles, so we're just going to step through these. First, there's evolve to survive, which is defined as the ability to continually incorporate and embody information to ensure enduring performance. Notably, evolution or nature's design process does not have an intended outcome that allows survival. However, this principle emphasizes that a system must learn through strategies, such as replicating success, integrating unexpected information, and reshuffling knowledge. Next, natural systems adapt to changing conditions. They do this by appropriately responding to dynamic context through incorporation of diversity or maintaining integrity through self-renewal, and embodying resilience through ideas of variation, redundancy, and decentralization. Third, we see natural systems' ability to be locally attuned and responsive, integrating with the surrounding environment through tools such as leveraging of cyclic processes, using readily available materials and energy, utilizing feedback loops, and cultivating cooperative relationships. Fourth, natural systems have the ability to integrate development with growth. Biomimicry 3.8 attributes self-organization, bottom-up approaches, modularity, and nested components toward natural systems' ability to do this. Fifth, systems should be resource efficient, skillfully and conservatively taking advantage of resources and opportunities. Natural systems frequently use low-energy processes and recycle materials, and they also use multifunctional design and fit form to function. Sixth and last, natural systems use life-friendly chemistry by breaking down products into benign constituents, building selectively with a small subset of elements, and doing chemistry in water. These 6 principles bring insights into design strategies that have proven successful within living systems towards withstanding and adapting to stresses and shocks. Resilience is not a designed characteristic of a system, but an emergent property of a collection of design choices. Therefore, by integrating characteristics of natural systems that have proven to lead to the emergence of resilience, infrastructure managers may be able to foster and reconceptualize resilience in infrastructure systems. To do that, we need to understand how infrastructure managers have integrated resilience into design. Resilience does not have an agreed-upon definition in engineering, as was discussed earlier. However, Woods led an article in 2015 stating resilience as the ability of a system to respond to expected and unexpected stresses, or long-term disturbances like aging infrastructure, as well as shocks, which are abrupt disturbances like extreme weather events, within and beyond the engineered systems design envelope. And he attributed 4 concepts to this: rebound, robustness, graceful extensibility, and sustained adaptability. By reviewing literature, both in academia and practice, our research team identified recurring themes, or what we called core concepts, for resilient design. In practice, or in designs of infrastructure being implemented right now, today, infrastructure managers use core concepts such as robustness, which is the ability to withstand a disturbance, efficiency, redundancy, recovery, or the ability to return quickly to an intended function, and success of previous experience, which you may know as the status quo. Resilient infrastructure theory includes these core concepts found in practice, but the list is expanded. We see large concepts such as adaptive capacity, or the ability to change in response to new stresses and shocks, flexibility, the ability to meet changing demands, and agility, the ability of physical and institutional systems to maintain functionality and uncertainty. These overarching themes and end goal for resilient infrastructure are supported by more core concepts, such as anticipation, when a system can integrate knowledge to predict disturbances, cohesion, utilization of unifying forces and feedbacks, diversity, graceful extensibility, or the opportunity for infrastructure to respond to disturbances beyond its design envelope, holistic design, innovation, learning, resourcefulness, or the institutional capacity to respond to a disturbance, and sensing, which is the ability to recognize and understand new stresses. So, biomimicry is the emulation of nature and design, and life's principles allows emulation of systems levels or ecosystems. This is important because infrastructure is also a network of systems. Now that we have defined life's principles and explored core concepts of resilient infrastructure design, we will be exploring the different alignments, contradictions, contentions, and gaps that arose between these two frameworks. And what we found overall was that infrastructure resilience theory frequently aligns with life's principles. However, infrastructure resilience in practice does not always align and at times even contradicts life's principles. Let's get into some more of the details though. For each life's principle, I will be exploring its application to infrastructure design. First, evolve to survive. This principle is heavily represented in infrastructure design because infrastructure is designed not to fail. Survival or service of infrastructure is the primary measure of success. Engineers are well equipped to implement designs that have worked in the past, one of the sub-principles represented here. However, this does assume stationarity, or that the future will resemble the past. Therefore, one major takeaway from this principle is the ability to learn from failure. Design approaches that embrace this are emerging, such as safe-to-fail infrastructure, where the infrastructure is also planned and managed for a quote-unquote failed state. This could be a park that provides recreation most of the times of the year, but also serves as flood mitigation during a rain event. This flooded state could be considered a failure since the recreational services will not be in use and existing infrastructure might even break. However, this is seen as a management strategy when considering the whole city as a system, because instead of the surrounding suburb flooding, it will be just the park, and so now it's a manageable area. And this emphasizes the importance of a system of systems design. Second, looking at adapt to changing conditions, one way engineers currently prepare for changing conditions is to integrate redundancy into their systems. For instance, a power company will set up more than one pathway for electricity to move between the generation station and the end user. This way, if one power line goes down, the company can still maintain service to the customers. Redundancy is an aspect of resilience also found in natural systems. We can find other potential solutions for adapting to changing conditions, such as integrating multifunctionality into infrastructure designs. Think of your skin. It does more than protect your body. It allows your system to sense and heal as well. Our infrastructure can serve multiple purposes, such as the safe-to-fail recreational park and flood mitigation example just provided. This allows us to challenge what a failure is. Is it only when the technological system fails, or is it when the social, ecological, and technological systems fail? What if the social and ecological systems remain operating? Did your infrastructure fail? These are big questions that begin to arise. Third, we can look toward being locally attuned and responsive within nature. And this has provided muses in the past when looking at infrastructure design. For example, we have industrial ecology, xeriscaping, passive design. However, current practice shows one large contradiction, and that's robustness. Being locally attuned and responsive emphasizes the importance of cooperative relationships between infrastructure and the surrounding environment. But when we look back onto the history of our development with innovations of canals, railways, service lines, HVAC systems, humans have further disentangled themselves from nature, attempting to survive independently of the surrounding environment. But these are just attempts because nature provides us with a lot of different ecosystem services. And I'm not saying infrastructure managers need to devolve, but they should actively consider leveraging the cyclic processes and readily available materials, as well as feedback loops and cooperative relationships to help increase resilience. Fourth, integrating development with growth. Natural systems do not design with an overarching blueprint, but through modularity, with components evolving in conjunction, from individual species to communities with co-evolved members to complex ecosystems. Resilience emerges over time from the collective properties of the ecosystem components. Integration of development with growth rivals the lock-in, or the inability to change a system due to financial, political, technical, social, cultural, and even technological barriers. multipliers that is seen within most infrastructure systems. Infrastructure does not currently have the capacity to undergo this coevolution with social, ecological, and technological systems due to this lock-in. In short, as long as infrastructure is designed in a stationary manner, the system cannot be perfected to the surrounding environment because social, ecological, and technological systems are constantly changing. The fifth principle, be resource efficient, is something infrastructure managers are very good at. Infrastructure design seeks to reduce the resources and energy used to minimize cost. This principle, particularly the sub-principles of use low energy processes and recycle all materials, are represented in sustainability efforts. However, sustainability, which is commonly understood as the reduction of negative environmental and social impacts, does not promise resilience. It simply is one aspect as shown through life's principles. For example, LEED certified buildings, while effective at promoting sustainability, do not necessarily increase the resilience of a design. One thing infrastructure managers can consider here is satisficing instead of optimizing. Satisficing is a combination of the words satisfy and sacrifice, meaning you have to address the trade-offs from a social, ecological, and technological viewpoint, each appropriately. Last is use life-friendly chemistry. Now, this may seem irrelevant for infrastructure design, but this principle reminds us to build selectively, not using unnecessary or hazardous materials, as well as through modularity. By following these guidelines, the complexity of a project can be reduced, which can allow easier management by combating the convolution of legacy systems, where future managers may not be able to understand or have the tools necessary to fix the system. All in all, life's principles can help guide infrastructure managers toward more resilient infrastructure. The objective is not for every resilient infrastructure core concept to address every principle and sub-principle, but that infrastructure design addresses each of these principles and sub-principles through an amalgamation of the resilient infrastructure core concepts. Life's principles offer a snapshot of design lessons and strategies that have emerged and sustained life for over 3.8 billion years, and in the face of dynamic and often unpredictable operating conditions, which serves as an excellent role model. We all learned a lot through this project. So lastly, we are going to listen in on one more conversation between Dr. Sam Markoff, Dr. Sam Hayes, and myself to hear about our major takeaways.
So Alysha, through this project, you've been leading an exploration of how biomimicry can support resilient infrastructure design. Curious what a major takeaway of the work has been for you.
I believe one of the biggest takeaways for me has been the emphasis on a transdisciplinary approach and how it can provide guidance for infrastructure managers to design more resilient infrastructure. We don't need to reinvent the wheel per se. What was particularly enlightening is that resilient infrastructure design theory really closely aligns with life's principles, and this shows us that we're heading in the correct direction. We just need to work on transitioning theory to practice.
Yeah, and I think related to that, this project has really underscored the importance of effective science communication. Without that, it is extremely difficult to develop the transdisciplinary collaborations that are needed for the complex challenges of the 21st century. Additionally, effective science communication is often a crucial bridge between theory and practice. So Sam, how about you? Any major takeaways on your end?
Yeah, and building on what Alysha's just said, I think for me it was a really interesting reinforcement of what we already know intuitively, which is that there can be a real gap between advances in theory and the extent to which that makes it to industry and applied practice. And that was really highlighted in the work, you know, as the biomimicry principles aligned really quite well with the theory, but not as closely with what's happening on the ground. And there are so many reasons for that. One is just the passage of time, but it also reinforces, I think, the importance of really proactive collaboration between industry and academia to sort of bring these areas together.
Yeah, effective collaboration across academic disciplines and between academia and practitioners, I think, is crucial for the challenges facing our infrastructure and cities in the coming decades, and making sure that the infrastructure is as resilient and sustainable as possible. And I'm encouraged that a concept like biomimicry shows promise for enabling and enhancing such efforts. Alysha, How do you think the knowledge and experience you've gained from this project will change the way you approach infrastructure design in your work and research moving forward?
One thing I want to be is less scared of transformational ideas. Natural systems have tried an uncountable number of designs. However, as an early career engineer, it can be really scary to work outside of the norm. Civil engineers in particular really only get one chance to design infrastructure that will last for decades to generations. But I don't think that means we should limit outlandish ideas and possible designs really during the brainstorming phase.
Yeah, and I found for me, I really appreciated that the work gave us clear mapping of these biomimicry ideas to those more established concepts and practices. So as Alysha says, we can start to incorporate some of these, outlandish ideas in a way that is tied to existing knowledge, that we're grounding these in our existing understanding and research into resilience. We knew that there were connections, but we didn't really know the extent of those connections. So for me, I think in practice, it gives me a really good foundation to have the conversation with design and construction teams on future projects to say, here are a set of biomimetic design principles that can really help us to better align with where the resilience research is heading.
Definitely. I think it's exciting to realize that there's still so much that can be learned from natural systems and applied to the built environment. And equally exciting to think that we might be on the cusp of some major transformations in the way we think about and design our infrastructure systems. And the fact that infrastructure 30 years from now could look radically different than it does today. And so I think it's safe to say that we've all learned a lot throughout this research. So as we kind of begin to wrap up, Alysha, I was just wondering what you think the major finding is of this work regarding the use of biomimicry for infrastructure design.
We saw in our research a list of core concepts for resilient infrastructure design and a list of life's principles for natural systems resilience. While these lists were itemized, I think the big takeaway is that you cannot achieve resilience with only one of these concepts or one of these life's principles. Instead, you have to have this collaboration of all of them to work together dynamically inside of the system and between systems to truly achieve the resilience that we're looking for.
Great. Well, thank you both for joining us today, Alysha and Sam.
Thank you.
And there you have it, the end of this month's episode. Thank you for joining us today.
The Future Cities podcast is an outreach effort brought to you by the Urban Resilience to Extremes Sustainability Research Network, or UREX as we usually refer to it. To learn more about UREX, visit www.sustainability.asu.edu/urban resilience. If you have any questions, feedback, or suggestions for future episodes, you can email us at futurecitiespodcast@gmail.com or find us on Twitter at FutureCitiesPod. If you enjoyed the episode, please rate and subscribe to us wherever you get your podcasts. See you next time.